Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a concept in radioactivity. Of course, that is the process of radioactive decay. We had looked at some of the specific areas that are of concern, of course, which we need to know in order for us to be able to interpret this concept of radiation or radioactivity. And that one was the concept of an atom and some of the subatomic particles, and specifically the nucleus. So that one laid for us a basis or a prerequisite for us in trying to discuss these subsequent topics that are of course of concern in as far as radioactivity is concerned. So for today we're going to concentrate on radioactive decay and see different types of decays that result from this process and the number of particles which we are going to mention which come up to this process. So for that case, welcome to the discussion. So as I've said, today we're going to look at the decay processes. So basically radioactive decay processes. This is radioactive decay. And basically here we are going to look at how these radioactive processes, which is a radioactive decay, occur. So in that sense, we are going to just have a slight definition of the concept of radioactivity that we had given last time, and that is going to give us a clue on how we are going to approach this kind of discussion. So in an actual sense, we say that radioactivity, just going to list the main points. We say that the radioactivity is the spontaneous disintegration of non-stable atomic nucleus or atomic nuclei to form stable ones. And this whole process is accompanied with the release of energy and particles. Of course, these are new particles which are going to be formed. So this process is accompanied with the release of energy in form of electromagnetic radiation and particles. So in actual sense, when we try to look at the definition of the term radioactivity, we get some concepts from this definition in the sense that there is an aspect of spontaneity that is being mentioned there, which basically means that one cannot pinpoint what nucleus will decay or when it will decay. So that refers to the concept of spontaneity. And then we have talked about disintegration, which means basically that this thing is going to fall apart or split in some kind of that, of course, some kind of that aspect. So the next one is unstable, of course, which means this particular nuclei that are undergoing radioactivity have a form of instability in a way that, of course, we discussed about the nuclear instability that results from the imbalance of the nuclear and the forces and the Coulomb forces for attraction that we find in the nucleus. And just we give an illustration that, of course, in the nucleus there are protons and neutrons. And for this part of the atom to be stable or just to maintain balance due to the repulsive forces of the protons that are positive charges, the nuclear has nuclear forces which keeps them together. So if there is an imbalance in this kind of forces, then we're going to experience what we call nuclear instability, which we have mentioned in point number 3. So in this case, that's where the concept of stability stems from. And we're going to see that the different types of electromagnetic radiations or the radiations which occur due to radioactivity have different characteristics. And of course, lastly, we shall look at the particles which are formed from the decay process. Now, we may ask ourselves that this concept of radioactivity did not just happen, and it was a concept that developed over time. And a number of scientists tried to come up with the observations which were used to conclude on various aspects of radioactivity. So in this timeline, of course, there were, as I've said, various individuals who contributed heavily to this concept of radioactivity. And that the first one as the Henry. This is an becquerel. I hope the spellings are okay and the mentioning may be different way, but this individual, of course, observed that uranium compounds emitted invisible radiation, which was trying to work on the. We're going to see. We're going to see, of course, this element that is known as uranium, and try to see on how it is going to be involved in this concept of radioactivity. Of course, he was trying to work on uranium, and observed that uranium compounds emitted invincible radiation, which had the following characteristics. So one is that these radiations blackened photographic plates. And then a second characteristic of this radiation is that they were ionizing gases. They ionized the gases, or ionized the gas. And then number three is that the crystals, specifically the uranium crystals, this is crystals, the uranium crystals fogged photographic, they fogged photographic plates. So in actual sense, uranium crystals fogged photographic plates. These ones are also curious to try and find out the kind of radiations that are being emitted from this particular element that we're not calling uranium. And of course, this together with the other subsequent works of various scientists like Pierre and Marie Curie, who discovered the element known as polonium and radium, which are of course radioactive nuclei, contributed heavily to the development of the concept of radioactivity and radioactive decay. So in this case, they laid a basis for the foundations of other aspects of these particular elements like uranium that we have talked about, and some of the characteristics of this resulting radiation that occurred. So, and the work of course, trying to figure out the characteristics of the nucleus, and of course, Ernest Rutherford's contribution towards the concept of the nucleus, or just played a great role in understanding of the nucleus, in a sense that he was able to figure out that the plum pudding model that was of course proposed by Thomson was not actually the case for the structure of an atom. So he proposed this kind of an atom whereby the nucleus is centrally located, and the electrons are orbiting, of course the distance from the nucleus, they are orbiting around the nucleus, whereby the nucleus consists of protons which are positively charged, and then the neutrons, which are of course having a net charge of 0. So in this case, the works that we have mentioned lay a basis for us in trying to figure out the concept of radioactivity. And of course, we said that these processes can occur in various ways. So I'm going to list the number of processes, or a number of processes that, of course, we refer to as that take place under the concept of radioactive decay. Now, the first one is alpha particle, or alpha decay, alpha particles. So this is the release of alpha particles. And then the second one is the release of beta particles, which of course are denoted as this one and that. And then we have the gamma, the emission of gamma rays, or gamma radiation, which is denoted as such. And then of course we're going to look at the neutron radiation, and then there's a production of what we call a positron production, and lastly we're going to look at the concept of electron capture. So these are some of the processes that result from this concept of radioactive decay. And of course, these processes have different characteristics, which we're going to mention one by one. So in this case, we're going to start with the alpha particle, or the release of alpha particle, or alpha decay, which of course I've said is denoted by that. So this actual sense, in alpha decay, you find that a heavy nucleus emits an alpha particle, which basically is the helium nucleus. So whenever we are trying to refer to alpha particles, this is a helium nucleus. And this process for an element that we've already discussed in one of our videos in Introduction to Radioactivity can be represented as this, whereby this is the atomic mass number, and whereas that is the atomic number that is below there. This is the mass number, this atomic number, and essence. So whenever an element is undergoing alpha decay, you find that there's a decrease in the number of mass number by 4 and atomic number by 2. So that's accompanied with the release of particles, which are alpha particles that we've denoted as helium nucleus. So in this case, this process has specific characteristic in a sense, in that they are highly ionizing and they have weak penetrating power. Therefore, they can be stopped. So these ones are highly ionizing and they have weak penetrating power. Of course, we are going to look at different characteristics for this, but in essence, what I want us to understand first is this equation that is used to represent the alpha decay. So the second one that we're going to look at is the beta. So for the beta decay or the release of beta particles, we have this mass and atomic number, whereby we have said that the beta decay is actually electron. So we are going to have a beta decay. It's like this, of course, is an electron which is negatively charged. And therefore, for a beta decay, a neutron turns into a proton and emits a beta decay, and the nucleus changes to that of a different element according to the equation that we have given on the board. So in this case, this kind of radiation is moderately ionizing as compared to the alpha particles. And of course, they have a moderate penetrating power, and they can be stopped by a sheet of aluminium. So we can see that they are much more penetrating than the alpha particles. But of course, they have unlike alpha particles, which have high ionizing power, they have moderate ionizing power. So the third one that we talked about was the gamma radiation. So the gamma radiation is part of the radioactive decay. So for the gamma radiation, you find that after a previous decay, a nucleus with excess energy will emit the gamma particle. So the previous decay, which means that either the particle has undergone the alpha or beta decay. So you find that this radiation is released after a previous decay, and the particles are a form of electromagnetic radiation that we talked about. So that is why we are referring to them as gamma radiation. So this is a form of energy, a form of electromagnetic radiation. So this kind of radiation has a low ionizing but high penetrating power, and it can be soaked by many centimeters of this element that we call lead. So I'm going to give an illustration in summary of what we've talked about the penetrating power of these three radiations that we've mentioned. Now there's this fourth concept that we talked about when we did our list, which of course we said that it's a neutron radiation. Neutron radiation occurs in a neutron-rich nucleus that is occasionally one or more neutrons which are ejected. And these are emitted during the process of nuclear fission. This one means splitting. So in the actual sense, this fourth process that we've talked about, apart from the alpha, beta, gamma, neutron radiation is another form of radiation that occurs when the nucleus is undergoing nuclear fusion, which I've talked about the concept of splitting. For the case of positron production, this is the fifth process. Apart from alpha, gamma, beta, neutron radiation, there's what we call positron production. So for positron production, particles with the same mass as an electron but with a positive charge are produced. Of course, these ones can be regarded as we can look at this as an antimatter version of this is an antimatter version of course, an electron. And as we stated, of course, we represent an electron using this representation or notation, of course, for a positron to just be represented as such. So therefore, whenever we're writing an equation and then we have this, remember that this one is going to refer to as a positron. So that is for positron emission. And lastly, we're going to look at process number 6, which is electron capture, which of course we are going to see electron capture. Now for electron capture, we're going to see that this process occurs in an inner orbital, whereby inner orbital electron is captured, a new nucleus formed, which of course we're going to regard to as a neutrino. And this is accompanied with the release of what we call gamma rays that we've already discussed about. For these two processes of positron, of course, production and electron capture, there's a net effect in a sense that for electron capture, the net effect is to change a proton into a neutron. And for positron production is to change a neutron to a proton. So if you try to look at the now for this second processes for the of course for electron capture, as I've said, the net effect is to change a proton to a neutron. So this one is for electron capture. But for proton positron emission, the net effect is to change, of course, this one basically that we are going to call a neutrino, and this is from a proton to a neutron that we are going to refer to as positron. This is a positron production. This is trying to confirm that one. Basically, by just using an illustration to give this concept so that we can be able to understand the concept. So in this case, I'm going to start with the first one. So these different types of radiations can be illustrated in various ways. And as I've said, of course, for radioactive nuclide that is undergoing decay, there are various products which are going to be formed, and I'm going to use this particular concept in order to illustrate that. So in this case, there's one type of radiation which is emitted, which is the gamma radiation, which we have denoted as such. And there's the beta particles and the alpha particles that are going to be emitted from, of course, a radioactive source. We had talked of an example for uranium-238. Of course, that is uranium-298. There's somewhere we denoted uranium. Remember, there was a wrong denotation for this. This is 238 uranium, of course. We'll be able to rectify that. So for uranium-238, that's got a mass number of 238 and 92. So it can be able to undergo this process, of course, or generally for radioactive. We're going to see specific elements are sources of different types of these three kinds of radiations. So specifically for this, we're going to see which product it forms. Now that there are different elements which we can regard as source of alpha decay, beta, etc., or gamma. So in this case, I'm going to use this one to illustrate. So suppose we have an radioactive source at that point, and 3 different radiations I've mentioned. So the beta particle is a high energy electron. Since we have mentioned their penetrating power, of course, it's a high energy electron. Now that we said that the beta particle is an electron, it is negatively charged. And for gamma radiation, this is a high energy electromagnetic radiation that can be able to be represented as that. And then, of course, we have the alpha particle, which of course we have said is a helium nucleus that is represented as that. So basically that's a general illustration for that. Now suppose we have a radioactive material like uranium that I've talked about. We can give an illustration and try to show how this decay process occurs and which are some of the particles and the products which are formed. So I'm going to give that example still of uranium-238 and 92, decaying to form an element that is known as thorium, which is represented as that. So there will be a net change in the mass and atomic number after it has lost what we call an alpha particle, which we have said is a helium nucleus. So in this case, of course, we said that gamma radiation happens due to a subsequent decay. So therefore, for that second decay, we shall have a radiation which is a gamma radiation, which I'm going to denote as gamma, as that. And then we have still thorium, which is still a mass number 238 and 92 for atomic number. So in this case, this second or subsequent decay happens due to instability, whereby there is a release of energy for the element to try and gain stability in actual cells. So this kind of decay series is what we call of course, this is a decay series for uranium-238, which can be represented as that. So some elements can just, in case this compound is unstable, still it will continue having subsequent decays until it gains stability, maybe by forming a stable element. Now this is for alpha decay. For beta decay, we're going to see that it has 2 different types of decay. We have beta positive and beta negative decay. So for beta decay, we have beta positive and beta negative types of decay. Now for beta positive decay, this is a formation of what we call an electron. Now that we say that the beta particle is an electron, beta positive is a formation of an electron where a proton changes into a neutron. So the proton changes into a neutron in this process. And for the second one, that is a beta negative or a beta minus decay, is a neutron changes into a proton. So a neutron changes into a proton. So basically these 2 processes, one is a reverse of the other. That is how we can be able to simplify them. Now I'm going to give an illustration for these 2 processes, for the beta process or beta decay, and this is radioactive decay process, so that we can have a better illustration for what those 2 processes entail. So the first one for a beta plus decay, I'll have an element, this is a carbon, with that, of course, a number. We said we can denote carbon, maybe carbon 12, using that one. So if an element is given as such, followed by having a number, this one indicates that this is cobalt 60. So therefore, whenever I'm writing C10, it implies that that is the mass number of that specific element. So if it undergoes decay, a beta decay in that case, we're going to have boron plus what we call a neutrino, which is represented as that, plus a positron, which is an positively charged electron, so or an antimatter for an electron, which is going. So this is a general representation for carbon forming boron, and then there's a formation of a neutrino. This is known as a neutrino. This is a neutrino. And then there's a positron, which is a positively charged electron at that particular point. This is for the beta plus process. And then for beta negative process, I'm just going also to give an illustration. We have an isotope. This is a carbon 14, which is undergoing beta minus decay. We shall have boron 10, and then that's a neutri plus an no, this is not going to be boron, of course. This is going to be nitrogen 14, and then we shall have that one plus an electron. So basically, if you try to look, this is a reverse process of this. This is a neutrino that is formed, but this is a neutrino that is formed at this point, but this is an anti-neutrino that is illustrated using that bar over there. So therefore, we have positron, electron, and this is a formation of these various products. This is boron that is formed at that specific point. So if you try to compare the two processes for the beta plus and beta minus processes, those are part of the beta decay processes that we experience in radioactivity. Now, there are different characteristics of the various radioactive processes that we are going to mention. Of course, after a discussion, of course, of the two main processes that we mentioned, which is positron production and electron capture, which we need to also have this specific one. So we have positron production as one of the decay processes that occurs. So in this case, we said that for positron production, in this case, as we've said, particles with the same mass and as an electron, but with a positive charge, which we refer to as a positron, of course, are formed. And the net effect is to change a proton to a neutron. So I'll just give an example of an illustration of what occurs, that is that particular element, which is sodium. This is forming a positron, a positively charged electron, and that outer nuclei that is having a mass number 22 and 10. If you see the difference between this one and this one, there's a net effect, of course, which is to change a proton into a neutron. So in this case, we can just illustrate this process by using maybe an illustration, just to do away with this. This is an element, of course, that is undergoing this kind of decay, and then we have this. Basically, at this point, is a nucleus that is experiencing or having a photon. We talked about a photon as a packet of energy, so in this case, it's going to undergo this process that is going to result in the formation of an electron and a positron. So this is going to be, of course, this is negative. So in this case, for the positron production, this is the process that we are trying to refer to. So lastly, we shall look at the electron capture that we have mentioned also as part of the processes that occur during this radioactive decay. So I'll just use also an illustration for an element that is carbon steel, which is carbon plus an electron. So this is electron capture that I'm trying to illustrate. So this is due to the formation of boron 11 plus a neutrino. So we refer to this one to as antineutrino, so it's leading to the formation of a neutrino and that product. So this is carbon and this is boron plus a neutrino. So in this case, if we try to look at this particular case in an essence, you find that for this one there will be 6 protons and then there's 6 neutrons, and these two basically will form what we call nucleons. They are found in the nucleus, so they form what we call nucleons. But for the second one, there will be a difference in a way that there will be 5 protons, but there will be 6 neutrons. So in that case, there will be an additional number. This addition, wherever this is the first process for the protons, is subtraction. So there's a loss of a proton, there's an addition of a neutron. So basically, this whole process refers to the concept of electron capture that we have, of course, talked about. So lastly, we are going to look at different characteristics of these types of radiations and some of the ways in which they can be able to be identified whenever there is a process of radioactive decay. So I'll start with the gamma rays, or maybe just give a general illustration so that it can assist us in order to try and explain how various radiation products can be able to be identified. So I have that. This is an illustration I'm going to draw. This is negative, this is positive, and then we have this basically is an electric field that is going to be created due to the presence of those two charges. And then this is a lead shield. When we are trying to illustrate the penetrating power, we just try to see the essence of this lead shield that is here. And this is a radioactive source. And then for this case, we shall have a different behavior of the radiation that is coming out of there. So this illustration was done, and it was observed that whenever this source of course, a radioactive source was subjected to an electric field, there was a characteristic behavior for different types of radiation that was produced in a way that the first one was deflected towards the negative part of that electric field, or maybe the negative charge of that part of an electric field. Basically, from the Coulomb's law of attraction, we can infer that this one, being attracted to the negative charge, is a positively charged particle. Therefore, it was concluded that this is the alpha particle that is emitted towards that point. And then there's one that is not affected by the electrical magnetic field, and this is the gamma radiation that was concluded to be that one. And then lastly, there's one that was attracted towards the positive part of the electric field, and basically that one, due to the laws of attraction, it was concluded that it's a negatively charged kind of radiation or particle, and therefore that is the beta part of the electromagnetic radiation. So in this case, those are some of the different characteristics that we have talked about. Now the last example is going to give us, of course, a concluding remark on how this, or the summary of how these radiations can be able to be described, or their different properties. So in this case, I'm going also to have an illustration to try and show that one. So we have this first. It's just basically a block. So therefore, the first one, we have what we call the alpha particle, the beta particle, the gamma radiation, and the neutron. So I've not indicated for the electron, but we just use basically these ones to represent a wide range of what we have talked about, the ones that have got specific characteristics. So for alpha particles, we say that they have velocities that are ranging Okay, of course, we're going to see this is just a penetrating power of various radiations that we have talked about. So for alpha particles, they can be stopped by a thin sheet of paper. This is the first one that we have illustrated. Now for beta particles, they can be stopped by a sheet of aluminium. And then for gamma rays, they can be stopped by, that is lead, the block of lead that we have indicated there. And therefore for the neutron, they can only be stopped by this block of concrete that I've shown on the last end part of the board. So in this case, this one gives us a different ways in which we are going to look at different kinds of radiation from radioactive decay, in a sense that they have different penetrating power that I've illustrated on the board. Now lastly, I'm going to look at the summary of the three that we have discussed, so that we can be able to close on this discussion on radioactive decay. So for the first one, the alpha, beta, and gamma that we have tried to show using different illustrations. For alpha particles, which we have given as helium nuclei, which are positively charged. Of course, we have said that they have the velocities ranging between 1.4 to, this is 1.4 to 1.7 times 10 raised to, times 10 raised to 7 meters per second. And that's a speed that is almost ranging or comparing with the speed of light. And they have high ionizing power. They have high ionization energy. And we talked about during the discovery about the concept of a photographic plate. So they have a visible effect on photographic plates. Visible effect on photographic plates. And then they can be able to, they are scattered by, of course, whenever they are traveling, they can bombard other elements, but they are scattered by nuclei of heavy elements such as gold, etc. They can be scattered by heavy elements such as gold, etc. So in actual sense, this kind of radiations can be produced from a radium source. So the source for this kind of particles, one of the examples is a radium source, and that is radium 226. Just a great here. Radium 226 is a source of the alpha particles. And then we have the gamma rays. We're going to look at a summary of different characteristics of the gamma rays that we have already discussed. So number 2, we look at the gamma rays. Gamma rays. So the first characteristic for gamma rays is that they are electromagnetic radiations of shorter wavelength, or of short wavelength. Just use it. Just going to use lambda for the sake of space. So there are electromagnetic radiations of short wavelength, which range between 0.005 angstroms to 0.5 angstroms. Of course, this division times 10 divided by 10 raised to 10. That one gives an angstrom comparing to a meter. So they are not charged, therefore they are not affected by the electrical magnetic field. So they are not charged. These particles or radiation are not charged, therefore not affected by electromagnetic radiation. So they travel at the speed of light, or maybe you can write to one decimal place. So they travel at the speed of light, and then they produce fluorescency. That's a glowing effect. They have produced fluorescence. I've said this is a glowing effect on some materials like phosphor. So in that case, and then they have more penetrating power than beta particles that we have discussed, and thus they cobalt 60 that given as an example somewhere is a source of the gamma rays. So lastly, we're going to look at the characteristic of beta particles. So beta particles. For beta particles, they possess of course, a negative charge and a mass that is equal to an electron. So we give them as this one. So their mass is equivalent to that of an electron. So their mass is equivalent to that of an electron. And then they affect photographic plates. They affect photographic plates. And then, of course, they produce fluorescence, as we have mentioned, for the gamma rays. And they are deflected. Now that they have charge, they are deflected by either electric or magnetic field. And they have high penetrating power compared to alpha particles. High penetrating power compared to alpha particles. And then lastly, strontium-90 is a source of beta particles. Strontium-90, this is a source of beta particles. So in an essence, as we of course I'm aware that we have just used that a little bit faster, but it's because of trying to look at these two different aspects of and the characteristics of these different aspects of the electromagnetic decay series, or just the decay process that we've talked about. So in that case, we shall just stop there, of course, and try to pick up when we're going to have another topic. Maybe we can have a recap of 1 or 2 of what we've discussed in that specific topic, which we're going to cover next time. So for that case, bye. That is it for today. Thank you.